Welcome to our talk about the Tverberg theorem, which is a result about partitioning point sets. This is the work of Aruni Choudhary and Wolfgang Mulzer. Let us start by recalling what the Tverberg theorem is. It says that, let's say you are given n points in d-dimensional Euclidean space and you want to partition it into k sets t1, t2 up to tk, where k is a natural number given as input, such that if we take the convex hulls of the sets in the partition, they have a non-empty intersection. The theorem says that if n is sufficiently large, if it is greater than this quantity over here, then it is always possible to find such a partition. For example, this is a point set in the plane, and this is what a two partition might look like. Since we have enough points, we can even get a three partition. But since there are not enough points for four partitions, we might not get a partition into four sets such that the convex hulls are intersecting. In fact, this is the maximum number of sets that you can have in a partition, and this bound is tight. For two partitions, you might already know this result as Radon's theorem, which is an older result. The computational problem asks, can we find such a partition such that the convex hulls are intersecting? This is what we call a Tverberg partition. If there are enough points, then it is always guaranteed to find such a partition. So this search problem is total, and this lies in the complexity class which goes by the name TFNP. More precisely, it lies in the intersection of two subclasses. Also, no efficient algorithms are known to find such a partition. What if we want more than n by d plus 1 partitions? In this case, Adiparasito, Barani and Mustafa showed last year that we can still have some approximate notion of Tverberg's theorem. Given any k, we can find a k partition such that each set of the partition has its convex hull intersecting with a ball, and the radius of this ball is dependent on the diameter of the point set times root over k by n. It is natural to expect that as k grows larger, the ball will also need to grow larger. So for our point set from before, this is what the result might look like. Here we have a 5 partition, and the convex hull of each set in the partition is intersecting this ball. Note that here there is no restriction between the relation of n and d. So this result is rightly termed as no dimensional. Another way to interpret is that the exact theorem talks about a common point in the convex hull of each set, while here we have a ball that intersects each set. They also showed that the bound is tight asymptotically. A similar result was also shown for a colorful version of the Tverberg theorem. The proof of this result is based on an averaging argument, which is randomized. You might wonder whether this can be de-randomized. Well, it can be, but at a very high cost. That is 2 to the order of n, which makes this impractical. On the other hand, the authors also gave a no-dimensional result for the colorful Choudhary theorem, which is based on a similar idea of averaging, but this time they can give a very fast algorithm. Let us recall what the colorful Choudhary theorem says. So in d-dimensional Euclidean space, we are given d plus 1 point sets, interpreted as colors. For example, here we have 3 colors in the plane, such that if we take the convex hull of each color, they have a common point, which is the red point over here. The theorem says that we can always find a colorful simplex, that is, which contains one vertex from each color, such that the convex hull contains a common point. For the no-dimensional version of this theorem, it is quite easy to find a colorful simplex, but the same cannot be said about finding a no-dimensional Tverberg partition. Which brings me on to our contributions. We in fact give a very fast algorithm, that is linear in n, to compute no-dimensional Tverberg partitions. We also give a fast algorithm for the colorful version of the no-dimensional Tverberg theorem. We also have a result, a no-dimensional result, or something that interpolates between the center point theorem and a generalized version of the Ham-Sandwich theorem. In essence, we are building upon this new notion of no-dimensional approximations. And for these problems, the exact complexity is not well known, but the no-dimensional versions are computationally easy. That's what we show from our result. The starting point for our intuition is a constructive proof of Tverberg theorem using a colorful character theorem. So this theorem also reduces the search problem for Tverberg theorem into the search problem of the colorful character theorem. This was made possible by Sarkaria's tensor product, which was later simplified by Barani and on. We define the notion of this tensor product. Then we apply an averaging argument on a colorful character theory instance that we create using a randomized argument. And finally, we show that this randomization can be dealt with in a very fast time. Our main contribution is defining this tensor product. So let us first understand what a tensor product is. Let's say we are given two vectors, u and v, this in m dimensions and this in n dimensions. The tensor product of u and v can be represented in this form. So we take the first component of u, that is u1, and we multiply it with each component of v and append them together. Then we take the second component of u, that is u2, and we start multiplying it with each component of v, and so on until we get a vector that is of m times n dimensions. This essentially contains all terms of the inner product of u and v. The tensor product is bilinear. Let's say that our input p consisted of n points p1, p2 up to pn. We are going to do some tensor products on p. For that, we take a set q of vectors q1, q2 up to qk, all of which are of the same dimension. You will see in a moment how these vectors are chosen. Now let's do some tensor products. So we first take the first point p1 and do a tensor product with q1. Then we do a tensor product with q2, and so on until we get a tensor product. We call each of these points as a clone of p1, and we collect them all together in a set called capital P1. We do this for each point of p, and then we get clones of p2, p3 up to pn. Now, we actually choose these vectors q1, q2 up to qk such that if we add them up, we get the origin, which also means that the centroid of these points is the origin. Now, applying the linearity of the tensor product, we find that the centroid of P1, P2 and up to Pn, all of them are the same. This is the origin. The next question in your mind would be, how do we choose these vectors, the set Q? We do that by the help of a graph. So we take a graph on k nodes, and each vertex of the graph will correspond to a unique vector in the set. The edges of the graph will correspond to coordinates. For example, we take this binary tree over here. Let us orient the edges in an arbitrary fashion. And now to each vertex, I assign a unique qi vector. Now we see that there is an edge that goes from q1 to q2. So in one component of q1, we put a 1, and in the corresponding coordinate of q2, we put a -1. We have an edge that goes from q1 to q3. So we now take a new coordinate, put a 1 for q1 and a -1 for q3. We do this for this edge that goes from q3 to q6 as well. So we have a 1 in a new coordinate for q3 and a -1 for q6. We do this for each edge in the graph. And for the remaining coordinates, we simply assign them as 0. Note that if we add up all these vectors, we get the origin, which is what we wanted. For this special set of vectors, we note that the dot product of any two vectors is -1 if and only if they form an edge in the graph. Remember that if two vectors don't form an edge in the graph, then they do not share a common coordinate in which their components are opposite of each other. These are vectors in the dimension that is the size of the graph, that is the number of edges in the graph. The squared norm is the degree. Why are these vectors important? These are important because the set Qi will correspond to the set Ti in the partition that we form. Next, we look at a useful equation that we get from the properties of these vectors. Let's say we are given k vectors u1 up to uk, all of the same dimension, and we compute this tensor product. So u1 has a tensor product with q1, u2 has a tensor product with q2, and so on. Let's say we want to add these products and take the squared norm. Then this is actually equivalent to looking at each edge in this graph and taking the squared norm of the difference between the corresponding vectors. This is possible because of the special structure of the vectors that we choose. So we introduce this notion of choosing these q vectors based on a graph, and that is what constitutes our refinement phase. Let us now look at the averaging argument. Recall that capital P1, capital P2 up to capital Pn are the clones of the input point set, and the centroid of each set is in fact the origin. This sounds very much like the colorful Choudhary theorem, but that theorem does not apply here because the number of point sets and the dimension of the space has no correlation. That means if we take a colorful simplex, which we call a traversal, then the convex hull of that simplex may not contain the origin. However, if we look at the centroid of the traversal and we take the expected value of the squared norm, the centroid, we can show that this is small. This involves a bit of calculations, and here the structure of the graph becomes quite handy. More precisely, this expectation can be bounded by this quantity over here. The square diameter of the point set times size of the graph divided by something that depends on k and n. From this, we can argue that there exists some traversal where the norm of the centroid is at most this quantity over here. We will now use the traversal to find a partition of the original point set. Remember that the traversal contains clones of the input point set. So it might contain some clone of P1, some clone of P2, and so on. You can group all the first clones together, and this forms the set P1 in the partition, and so on. So the kth clones will form the set Pk. Now we want to show that the convex hulls of the sets the partitions are closed. More precisely, we will show that there is a ball that contains the centroids of each of these sets, and that ball has a small radius. What we already know from our calculations is that there is a traversal for which the centroid has norm at most comma. Let us now bound the radius of this ball. So in fact, we can choose our set such that the size of each set in the partition is the same. In this case, the centroid of the traversal can be expressed as tensor products of the centroids of the sets in the partition. Next, we plug in the relation that the norm of the centroid is at most comma, and we get this. Now this expression looks similar to our equation from before. So we have our tree, and we can now replace the ui vectors by the centroid of the ti set. Then this expression can be simplified to this form, where we go over the edges, we look at the centroids of the corresponding sets in the partition, take the squared norm. After some more calculations, we see that if we take a ball with centroid of T1 and radius this quantity, then it contains every other centroid, and this is the ball that we are looking for. So the radius depends on the diameter of P, k by n minus 1, which is a fixed quantity, and this quantity will depend on the graph. This quantity is not minimized for a binary tree, but rather a star graph. By plugging in the values, we see that the radius is about k by root n times diameter of P. This is in fact a factor of root k worse than the result of Adiparasito, Barani and Mustafa. Using similar arguments, we can also get a radius bound when we want that the sets of the partition T1 up to Tk have a specified size. This summarizes our averaging argument. Next, we look at how we do a de-randomization of this argument in a quick manner. Simple way of de-randomization would be to use conditional expectations. What does this mean? We already have an upper bound on the squared norm of the centroids, expected value. Let us look at xn. This is one of the clones of Pn. We substitute the value of the first clone, compute the conditional expectation, and check whether this is less than the expectation without the condition. We do this for the second clone and the third clone, and so on until the kth clone. For at least one of these clones, this conditional expectation is less than the normal expectation, so we pick that clone and call it yn. Next, we focus on xn-1. This is a clone of Pn-1. To find this, we fix yn and we fix the clone for xn minus 1, and we recompute the conditional expectation for every clone of tn minus 1 until we find some clone which has a lower expectation than the standard expectation. We do this for each point, and in the end we get fixed assignment of clones for x1 up to xn, and that is the required traversal. In fact, we can compute these conditional expectations quite efficiently, so we do not have to compute the tensor products. And to avoid that avoids pitfalls associated with working in a high dimensional space. This algorithm gives a running time of n times d times k, which is fine, but we can make it faster. In fact, we can reduce k to log k, so our simple algorithm can be made much faster. What is the intuition behind this? Remember that when we choose a clone for pi, we are cycling through each clone of pi, and that takes order of k iterations. That is how the factor of k appears in the running time. We can, however, use a smarter way to find this clone that involves building a tree where each node corresponds to a q vector, and then finding an appropriate clone of pi involves picking one of the vertices of the tree. We augment this graph with some additional information, and that helps us calculate this conditional expectation quickly. To find a suitable clone, we simply have to start a walk from the root and go towards the leaf. Along this path, we find that at least one vertex satisfies our requirement that the conditional expectation is lower than the regular expectation. After we pick the clone, we have to update some information in the graph, but that only affects nodes which are along the path or neighbors of those nodes. So, since the left of the tree is log k, we spent log k iterations in finding the clone. To summarize, we gave a refinement of Sarkaria's tensor product, and we used that to find new proofs and very fast algorithms for no-dimensional Tverberg partitions. There are two more results about which we did not talk about in our slides, that is the colorful Tverberg partitions and interpolation of the center pointed generalized theorem. They also follow kind of the same workflow. There are some open questions. The first is to improve the radius bound for Tverberg partitions. As we saw earlier, it is root k times of the optimal. Then, colorful Tverberg uses a more sophisticated tensor product. And for that, when we de-randomize, we really have to spend n times d times k time. So it remains an open question if this can be improved. Another possible avenue would be to find new applications for this refinement of Sarkaria's tensor product. Thank you.